So what we are going to do this afternoon, before we do the model calibration validation, is we are going to go a little bit over how do we set up the watersheds, the different sub areas, or if you want, how do we connect two fields together? So in order to do that, the first thing that you need to take a look at is this description that we have in a figure number 2 in the user manual. This is an illustration in which it's going to help you understand how actually the routing works. When you try to connect two watersheds or two sub areas or two fields together, actually what you are trying to do is to tell the model how the routing should happen. And to understand that, there's a couple of things that you need to know. First is that Apex, in the case of this small sub-watershed, we have 1, 2, 3, 4 different sub areas. Or if you want, you can have a little farm that has 4 different fields. So in the case of the sub areas, we have what we call upstream sub areas. An upstream sub area like number 1 and number 2 is the one that does not receive any water from outside or above. So in other words, this is where the routing is going to start. And as you can see, in this case, we have 2. And then from what happens is that water will be accumulated, will be moved at the beginning of the channel, and then it will be transported all along. Same thing here. It will come here, and then it will be transported here. In these channel processes, you will have things like deposition of solids, evaporation, and so on and so forth. So the model is going to start routing things here. So how do you know which of these events happen first? So in this case, you need to take a look at this part. One of these sub areas first has to pass the values to the other one before these two go to the next. So at this point, you are going to have the whatever is transported from here, whatever is transported from here, and before it joins to the next, it goes to the next, they are going to, one of these is going to pass the values to the other one, is going to do a sum up, and then is going to route to the next. So how do you know which of these ones is going to be the donor, let's say, to the other one? And you set it up with the watershed size variable. If it's negative, it means that the information is going to be added. So in this case, if number 2 is the negative, it means 1 is going to pass the values first to 2, and then when 2 is here, it's going to put it all together and then start routing downstream. Because these are just one sub area or one field, one sub area, one field, it's going to just go to the next and then to the next. Okay, so there's a little difference in Apex in SWAT. In SWAT, when you do the transport, you do the, let's say you dump everything at this outlet. In the case at the end of the channel, in the case of Apex, you do that at the beginning of the channel. So then you can have all these processes of transport, deposition, evaporation happening here. So that's one thing. The next thing is how do you know it's a headwaters or a downstream sub-area? The way that the model recognizes which is that, like in this case, you can see that, let's start here. In this case, you have the rich channel and the longest path to the furthest point in this watershed. And this is the blue dotted line, and we have this red and periods line here. In the case of upstream, they are equal. So in this case, they are one on top of the other. That's why the model recognizes that because these values are equal, then it identifies as an headwaters or an extreme sub-area. In the case of this other one, what happens is that there is difference. This is shorter than this. Therefore, CHL is going to be different than RCHL. Therefore, the model is going to identify this as a downstream sub-area. Same thing here. This is shorter than this. Therefore, this is a downstream, so it's going to receive whatever is coming from here. Finally, it gets to the outlet. So the outlet of sub-area 4, it's also the outlet of this small watershed in this case. And if you are working on fields, a collection of fields, then this is going to represent the out of the field in which you can collect and measure some of the outputs. So this is the conceptual part of how these different watersheds and sub-watersheds get connected. So what we are going to do now is we are going to make a demonstration. How can you make a connection of this? First, let's do something simple. One headwaters, one downstream sub-area. How do you make sure that the water is flowing from one to the other? It's going to be like the situation that if only have 3 and 4. How you make sure that this is flowing this way? Then we will try to add these two. So let's get to work on that. Luca, do you want to share your screen?
Or I don't know if you want to continue. I shared with you on the T drive a sub-area file with 2 sub-areas.
Okay,
It
let me
is
see.
on Luca to Javier.
Can you just place it on the T drive?
Yeah, it's there.
Oh, it's there.
It is on T drive, my folder, and to Javier.
Okay, let me stop sharing this and change Windows. Where is this other one? Let's make it small so anybody can see. And there we go. So you said sharing screens. You said you put it here.
My folder.
Oops. Where's Luca?
Yep. To Javier.
This almond?
Yeah. It
Okay.
is 2 sub-areas.
Copy. And we want to put it in the almonds. Let's put it, oops. Let's place it here, paste. Let me catch this because I will need it. And then let me open this. I pasted the path to the data, and then I went ahead and opened all the files just in case. So now let's go to the sub-area file. The sub-area tab here, again, I need to call my files, and it says this is the one. Let's start with this one, and let's see how it looks like. So this is the example that you were working this morning with Luca. It's a one sub-area file. So let's see some characteristics about the reach and this kind of thing. So let's go here a little bit more. Yes. So because we have just one sub area, you can tell that this is the sub area, the area, it's positive, so no problem. Now we said that let's see the CHL and the RCHL, what kind of values do they have? So in this case, they are equal. Whenever you work with one sub area files, or what it could be one field, just one field, like in this case, it must be a headwaters. It has to be the CHL and the RCHL, they must be similar, because that tells the model is one sub-area and this is it. Okay, so now let me show you what happens when I have two sub-areas. Now I'm adding two sub-areas to my work. And first off, the sizes are different. One is 10 hectare and the other one is 5. That's okay, no problem. What does it tell me? Because they are not, none of them is negative. What it tells me is that these two fields or subwatersheds are one after the other. They are not at the same level. You will use the negative only in those cases in which the two fields or the two sub-areas are at the same level. So the model doesn't know which ones comes first. In that case, you have to tell the negative is going to be the one who will be transferring the values first, and then that will go next. In this case, I read it that it's like you have one field here and then another field underneath. So this is connecting. So let's take a look at the RCHL and the CHL. In the first sub-area, because it's a headwaters, the values are the same. That tells the model this is a headwaters. There's nothing coming from above. This is where everything starts. And as you can tell in the second one, the RCHL is lower than the CHL. There's a difference. They are not equal. This tells the model this is a downstream sub-area. And because they are contiguous, it's telling this one will pass to this one. And that's why how it gets routed. So this is the way in which you will be setting up this kind of the connection between two fields. For instance, if you want to do a corn field, but then you want to do a best management practice, you want to do a conservation practice, you want to put at the border of the field what's a riparian buffer, for instance, then you have to set it in this way, in which this is the cornfield that's upstream, and then it will route everything from here to this next one, which is the riparian buffer. Obviously, you will set up these values these parameters for the sub area accordingly, like to represent a riparian buffer. Also, your management file has to account for, if it's a riparian buffer, you might need to have some grasses planted there, some trees perhaps, or some brushes or shrubs. So it will mimic the function of a riparian buffer. But the main thing I'm trying to make a point here is when you want to connect this to this, you need to use this difference. Headwaters, where everything starts, these values, these two values are the same. Let me color code it. This as, let's use blue, and this also blue. So these two, in this case, are the same. In this case, in the receiving one, or the one that is downstream, it's not going to be the case. This is going to be one value, and this other one is going to be a different value. So this is not equal to this. Therefore, this one is receiving. If you have another one like this downstream, then you will have to do the exact same thing. The way you connect it is that first, you will have another column here, and again, these values must be different. That's why, because it's sequential, it's going to understand from this field, or goes to this field, goes to this one, and so on and so forth. This is the way in which you have to set up your routing for Apex. And it works the same, is the same concept with a sub area or with a field. When you try to connect two fields, three fields together, this is the same concept that you will have to manage to do that. Questions?
I had one question. So at the file name, we have almond2ca. I think I don't have that file.
No. Yes, you are correct. You don't have this. I'm going to
Okay.
add it to the Google Drive in a minute, so you can download it and play with it. This is something that we consider it was important to answer a question, and that's why we pulled this one.
Oh,
But
okay.
I'm gonna make sure you guys have a copy of this too.
Perfect. Perfect. Thank you.
Cool. Questions about this? If not, let's move on. Let me stop.
We have
A question?
I can agree well.
Yes. Yes, sir. So when we make blue and red signs, then automatically model will recognize, and then it will connect hydrologically. If we colored like this red and then blue, then automatically model will connect these areas hydrologically.
That's correct, but it will connect it not because you color coded blue and red. It's because the values in this one are similar and in this one are not. That's what's telling you this is how to connect one to the other. Make sense?
Yes, sir. Yes, sir. Thank you. Thank you very much.
Okay. All right.
Moreover, Javier, I don't know, I just noticed one thing. I don't know if there is a little bug there, because the second subarea shouldn't be a headwater.
Yeah, that's what I noticed. I don't know what's going on. This should have been red actually until downstream, but
Yeah.
I don't know. There might be a bug.
Yeah. Well, for the people that is listening now, basically what is there on the, when you say headwaters, that is blue, this is basically is the tool that is putting those information according to the values that you have in WSA, CHL, and RCHL. You don't have to type anything here. As Javier is saying,
Yeah.
the connection is not because of these. or because of those two values there, or because it says add water. It depends by the values that you have in your subareas.
Correct. And if you look at your sub area, actually, what you are going to see is something like this. There's no headwaters, downstream, anything related here. So this is something that the model is trying to be helpful, trying to tell you, but for some reason it's not working. But the main idea is that similar headwaters, different downstream. If they are sequential, then this one passes water to this one. And with water passes all other solids as well, sediments, nutrients, and so on and so forth. Questions? No questions? Then let's move on. Let me close this. Let me close this. And let me share this. Is the screen up?
Yes.
Yes, Javier.
What we are going to do the rest of the afternoon is to work with how do you calibrate, how do you validate? In other words, how do you evaluate your model? How do you know your predictions are correct? How do you know the model is not just crunching numbers and spitting out some values? How actually can you make sure that the outputs of the model have actually a value? Because what you are going to do with the model is you are going to use the model to help people to make decisions. People make decisions at different levels. A farmer, a rancher will make decisions at that level. A politician that's in charge of making decisions at a different level, national level, policy level, in which is going to impact all of us, also needs these kind of tools that is going to help make better decisions. One powerful thing about the models is that you can play what-if scenarios. You can create multiple options, evaluate multiple alternatives that when you put side by side, it's going to help you out to decide which one is the best, or at least which one you should try on the real world. So these kind of tools are helpful in that way. However, when you need to be sure that your model predictions are correct, because there's one fact in modeling: garbage in, garbage out. The best way to guarantee that your model is providing good data is through characterizing the system properly. And that is based on good quality and quantity of input data. That's the best way to characterize the system. And then you need additional data because you need to evaluate the model predictions. You need to at least know how far are you from the real value, and also define what's the uncertainty that comes with the model. The uncertainty is something like a safety for all of us, in which we provide a recommendation, not as a fact, but we can say, based on simulation, this is the result, and this is the confidence interval in which we are sure that this is going to happen. So to do that, all of that, it's called model evaluation. Model evaluation will be 1 or 2 semesters at grad school, but we are trying to synthesize this in about 30 minutes. So let me go down. By model, when I refer to model evaluation, actually I'm talking about 4 different processes: sensitivity analysis, calibration, validation, and uncertainty analysis. When you work with models, likely you will do, you will have to perform all of this, at least at the beginning, until you become familiar with which parameters are sensitive or not. Then you will still need to do sensitivity analysis. Uh, then obviously you will have to do a calibration process, then a validation process, and I highly recommend you guys do uncertainty analysis as well. So, but we are going to see what are these. The concept of sensitivity analysis is what we are trying to do is to determine the rate of change in model outputs in relation to changes in values of the inputs of the or the parameters. In other words, how much the model outputs are going to change due to changes in input parameters. That is the concept of sensitivity. So what you are trying to determine is actually this rate of change in this figure. This solid black line represents the changes that happen in your model output due to changes in your model parameters or inputs. So let's say you have you set any meaningful parameter in the model to about five something. You run the model, and in your output or variable response variable, you will obtain a given value. In this case, close to 8. So then what you do is you change this value. You can increase it, you can decrease it. If you increase it, let's say to close to 8, you run the model, and then you capture how much is the output value now. So in this way, you are determining what's the rate of change in the outputs due to the changes in the inputs. Uh, this difference in the input values is causing this difference in your output values. In some cases, you are going to see that to big changes in input parameters, you don't get much change in your output. So then, therefore, you will call that this given variable or parameter is insensitive or slightly sensitive. So think about it. These kind of parameters that are insensitive or uh, slightly sensitive, they will not help you when you are trying to do calibration, because big changes will not create significant change in your model output. So this is why you do a sensitivity analysis. You are trying to determine which parameters of the model are sensitive or highly sensitive. So you can work with that when you try to do calibration and validation. So we have this case. The next one thing that you need to take care of is that you need to analyze the full spectrum of your model parameter values. Why? Because if you focus only, for instance, from 0 to 2, and you start doing your sensitivity analysis, changing the values, you can see and come up to an erroneous answer. Like in this case, it says, yeah, when I have this value about 1.4 and change it to 1.6, I obtain these big changes in my output variable. So it looks like it's very sensitive. But in another portion of the spectrum of this variable, you can see that even larger changes from 4 to 6 are not producing the same big response like you had before. This is why it's important to analyze the full range of your parameter values. In the case of Apex, where are you going to get this range? In the user manual. Each variable is going to tell you it grows from 0 to X. So then I will recommend you explore the full range of variables because these things can happen. You can set, if you analyze only this side, this portion, you can come up, yeah, it's not worth to work with this parameter. It's not that sensitive. Or you can do an analysis for this one and just say, oh yeah, this is good. But then when you do your simulations, not much changes happen. So that's why you need to, the take-home message of this figure is that you have to analyze the full range of your parameter values. Now, also you have to consider how your parameters change as a function or other changes in parameters. So you can have two different responses because you are changing another parameter. When parameter A is set up, for instance, to 2, you obtain this moderate change in this moderate sensitivity. But when parameter A is 3, then it could be that you observe the difference is, let's say, magnified. So all these factors need to be considered when you do sensitivity analysis. In the end, when we do manual this work manually, what we usually rely on is the relative sensitivity, which essentially is this equation. This is the observed value minus the base from the observed value divided by the predicted from the change in your parameter and the base parameter. That difference, this difference in this case will be, will be this minus this is what's going here. And the difference in your output is this. This minus this will go here. And then you have this, the base for the parameter and the base for the output variable. So this is what we call sensitivity analysis. Usually we multiply this times 100, and it's going to give you some values. And this is like a suggested table to classify parameters as insensitive to extremely sensitive. If your relative sensitivity gives you less than 0.01, this is insensitive. If you are in this case, in which this difference means almost nothing. While if you are in this other case, you might be looking to something like this, in which the changes are relatively big. So once you've done this, you will be able to evaluate and say, yeah, from this pool of variables that I'm interested in working with, I will use A, B, and C. F, G, and H are not sensitive or slightly sensitive. Therefore, it's something that I will not be, why should I waste time working with that when I know it's not going to cause any changes in the model? So this is the first step in your model evaluation. Then comes the concept of calibration. Calibration is the process in which you are trying to find a set of parameters that represent the reality in a better way, or a set of parameters that generate simulated outputs that are closer to your measured values. So I'm throwing here two concepts that says calibration is the process of determine a parameter set to provide the best representation of the system, or that minimizes the error between predicted and measured system response. So, as I said, in other words, we are trying to find what's the set of parameters that's going to generate that my model outputs are closer to the measured values I have. So in this case, when you work with a manual calibration, what you usually is, once you have selected the pool of parameters that you are going to work with, you change this sequentially. You change the values for the first parameter, and before you start running the model, you need to set up a criteria or a criterion in which you will run the model, and then you will evaluate if you meet or not the criteria or the criterion in this case. So let's say you change values here, you run the model, and you compare your outputs. Are your statistics good or not? If not, then you go back and move the next to the next. Run the model, ask, no. Again, you loop this until a point in which it says, yes, these changes meet the criterion. Therefore, you said yes, and the calibration is complete. In a simple way, this is how manual calibration works. And this is something that we are going to play with in a little bit. So this is a calibration. How do you determine the criteria or this against what are you going to evaluate? And here is where it comes into play what we call goodness of fit, the statistics that we are going to use to compare our values. The two that I like the most and I often use are the coefficient of determination, R squared. And we work with this. One thing that you need to know here is that the closest the R square value is to 1, it indicates that it's an accurate model simulation. And the closer it goes to 0, it's the opposite. And here you have the formula that you compare each observed data against the mean, and so on and so forth. So this is one of them. The other one is the NSE, the Nash-Sutcliffe efficiency coefficient. In this case, this is the formula, but these values goes from minus infinite to plus 1. Again, the closer to 1, the more accurate the model prediction is. And the opposite, when it goes to minus infinite, then you are far away from the real, the measured values. So this is, I like to use these two in combination with this table. This table is the one that you need, you can use to set up what's your threshold that you are going to simulate. Because when you do this, you run the model, you calculate your statistics, you compare the observed data to the simulated values, and then you can work with NSE, for instance, and you compare your NSE to what, and the what comes from here. If you want just a satisfactory level of your predictions, then your NSC must be between 0.5 and 0.65. If you want a very good simulation results, then your NSC must be from 0.75 to 1. But you have to set this value ahead. So you set your expectations before, you start doing this. you cannot just adjust this as you will. You need to set up your criterion or your criteria ahead. And says, what I'm expecting is a good simulation. Therefore, I'm not going to stop until I get my NSC between 0.65 and 0.75. There are, as you can see in this table, there are other statistics that you can use too, the RSR or the p-bias. But, this is something that you can use as a reference. And then you come here and you do your modification one by one. This is what we call a manual calibration. Automatic calibration, it's slightly different because you will not do the changes yourself. You will have an algorithm that is going to do the changes for you. You have to set the max and mean values for each of these parameters and let the model likely randomly pick one parameter, replace it, do the calculation, do the comparison. If not, comes, picks another parameter, selects a variable, and it will iterate many times. So in the end, you will find that eventually you will see if at what point you met this criteria. That's kind of the difference between automatic and manual calibration. If you do your comparisons at a yearly time step, I will recommend that at least you go with a good, you set your criteria to good. If you do monthly, then it's more difficult. Then you can work with, let's say, you can lower a little bit the expectation and work with satisfactory. But this is up to you. It's something that you need to define again at the beginning of this exercise. Questions up to here, up to calibration? No questions.
I can see someone
Raising
raised his
hands.
hand. Yeah. But I don't know if it was something.
Let me see.
I guess he was there.
No, believe it's from the past.
Okay.
So once you've done your stats, the first, always it's good to do plottings. Plotting is going to give you a visual idea of what's happening. Like in this case, when you do a stream flow, you can have this kind in 1 year looks close, the next year is not, looks close. This is almost identical. So when you do your statistics, you will have this kind of values. So in this case, this exceeds the expectations I set up at the beginning. Likewise, this, it's okay. It's setting up the expectations. So in average, what this number tells you is that in average, yeah, you can tell that your model is doing a good job. That's the purpose of calibration. So again, what you do with this is you are going to get a set of parameters, a set of defined parameters that you know now that you are doing in general a good job. So that's calibration. And then it will come the concept of validation. Validation is the process that demonstrates that a given site-specific model is capable of making accurate simulations for a different time period. Or if you want, is the degree to which a model is an accurate representation of the real world. So when you have in this case, a flow time series over the time, and this is what you want to represent and calibrate, usually you are going to discard the first years of the simulation. This is what we call an spin-up period. And the reason why we discard this is because this is a time in which we know the model is still adjusting internal parameters until they reach a steady state, so you can trust the simulations that you have. Then you can use one part of the time series for calibration to obtain the ideal set of parameters. And then you use the same set of parameters for a different time period. And then you evaluate with the same way you did before, but for a different time period. If likely, if you got, like in this case, I have 0.86, 0.76, when I do my validation, likely I would expect that those values will drop a bit. If they drop too much, then it's a sign that's telling you you need to go back and review your calibration because something is not correct. You might have missed a parameter to include in your calibration or something like that. Then you have to adjust it, work, repeat, and come back. You know the drill. You do the adjust here, check it. If it's good, then you have a tool that you will be able to use for making recommendations and helping people to make decisions. This is the difference between calibration and validation actually is that you use a different time of data for your evaluation. Same thing. These are my validation results, and as you can see, my statistics, they drop a bit, but still they are good. And this is expected because I did not use this data for the calibration. Therefore, I do not expect these values to be exactly the same or better, but still acceptable and they meet my criteria. So therefore, I can use this simulation model to respond questions like, what if I do this? The first thing is to characterize the system as it is, what you will call the baseline scenario, and then you can answer what if? What if I change this? What if I change that? And then you evaluate and you compare your variables until you find an alternative that is going to be the one that you are likely going to recommend or base your policy on that alternative. So that's validation. Again, it looks something like this. This is an example of that. And then finally, you have the concept of uncertainty. In simple words, uncertainty is the state in which you are not certain that something is as you expect, or something is not, it's similar to the real value. We are not talking about measured values here. We are talking about the real value. And the key of uncertainty is trying to approximate and telling you if your simulations are close or not to the real value. So then you have concepts like this is the inability to determine the true state of affairs in a system. Why? Because likely the real value is not known. So how do you approximate to something that's not known? It's based on a series of statistical procedures that are going to give you an idea of how far are you from the real value. There are different sources of uncertainty. You will have uncertainty due to the input data, because it happens that when things are measured in the real world, errors might come. So that will play a role in your simulations. You will have uncertainty due to our lack of knowledge of a specific event. We don't know enough about a given process. Therefore, we are not capable of mathematically represent that process. And maybe that's another source that's causing large uncertainty values in your simulations. Other is the set of parameters that you use for the simulation. Uncertainty in your output data, in your measured data. So it's not that just comes from one point. Actually, it's likely that's coming from all these sources here. One way to determine uncertainty is a Monte Carlo procedure. Essentially, you do the exact same you did for calibration, but you will use a Monte Carlo algorithm that will change the values here. You will do lots of simulations, and then in the end, you will be able to aggregate this data and calculate these values. Something like this, you will represent your uncertainty in terms of bands or area that tells you how much this simulated and observed are plotted here, and this is your results that you will be able to say, yeah, in this margin, in this time, this is how I'm certain or not that my predictions are good or not. This is the process of uncertainty, and I believe another way to represent it is with a modified Dropbox figure, in which you have the maximum, the minimum value, you have the median, the 25th and 75th percent of your data, and then you have the 90 and 10%. So then this is a way in which you can say, yeah, this is how variable my data is compared to these other values. It's another way just to represent how uncertainty in a different way. So we run, and this is, let's see, there's some questions in the chat box. Let me check. It says, oh, no, it's just Luca letting us know that the sub area is in the Google Drive. Questions?
Yeah, there are also two questions in the chat.
In the chat. Let me see.
Yeah. I can answer the second one. I cannot answer the first one because I have not prepared that figure.
Let me see. Let's start for the second one. Does Apex have a inbuilt tools for estimating uncertainty? No. The other question was, in year 97, the outcome of the observations and simulation looks quite bigger compared to other years. What's the expected reason? There's many things that can going on when these kind of things happen. It could be like, for instance, the first thing that comes to my head is that the time series for weather happens that in that year it could be something was wrong with the measurements, and it's causing that. Also, very important. Let me go back in this. When you do this model evaluation, you have to be conscious that the model is representing the data that you provided. And then you are trying to compare that to a data that was measured. Likely, both the measurements are inside they correspond to this field sub-area that you are trying to evaluate. But also, the weather variable is something that was collected, and it's directly related to these measurements. Because happens that many times, because lack of information, you collect data at the outlet, but your weather data is not even inside the watershed. So in that case, it's going to, obviously, the model will struggle to represent a situation like that. And those are things that you need to take care of. Let's see what else. Time distribution for one. What's the question? What's the recommended warm-up period? Is that what you guys are asking here? If so, this much depends on the length of your time series. For the case of the one of the projects that we have with NRCS here, we simulate 45 periods and we discard 15 as a spin-up period. But because we have sufficient length in our weather data to do such thing. And when you don't, then you need to do alternative things. But I would say that between 10 and 15 years is something that you should aim whenever you do this. Well, let's see, Susan. Oh yeah, Susan responded. Oh,
So just to
says,
add to what Javier has explained, and Sujan as well, uncertainty functionality is not available in any of our current tools. But the plan is that we'll be working with USDA ARS at Fort Collins, Dr. Lee Wang Ma, and Darren Hamill to add the uncertainty function to the Apex Qt, because Apex Qt does iterative simulation and collect outputs from Apex runs. We can introduce a formula to estimate uncertainty bounds and other uncertainty indexes within Apex Qt. So that is a planned work for this year. We are not there yet, but we are planning for it, and it is a planned task that will be accomplished later this year. So if you just wait a little more, then we'll have it available through the Apex Qt tool. And the pest U code is not really, I am not aware of any effort with the U code, but pest parameter estimation tool is the one that we recently developed Python code with for implementation. So pest is now available for calibrating coupled Apex and the ModFlow model, because Apex Qt can handle Apex calibration, but it doesn't cover ModFlow parameters. So what we did with Dr. Sungyo Park is that using Jupyter Note, you can follow the Python script we wrote to implement the pest, tool, parameter estimation tool, to concurrently calibrate and do sensitivity analysis and do uncertainty analysis of the coupled Apex ModFlow model.
very good. So there's one more question that says, which coefficients do you recommend for assessing uncertainty? That depends on what kind of output variables are you working with. And that's the answer for that is sensitivity analysis. You need to do a sensitivity analysis for the location in which you are working with and the data you are working with. And that's gonna tell you these are sensitive, these are not, and those are the variables that that's the information that you need to decide which coefficients or variables are going to use. Now, in terms of statistics, I usually recommend to work with the coefficient of determination and NSE. Others, they like to add RSR, p-bias, and so on and so forth. But if you ask me, I would tell you no, NSE and R square are enough. Because at some point, what other information these other statistics are going to give you? You need to analyze that. If there's something that some other statistic is going to add that might make you change your evaluation, then yeah, let's study. But if not, if all are going to tell you the same thing, then I don't see the purpose of calculating things just for calculating. So that would be my answer to that. Let's see, I can see there's more messages. Oh no, Jehak put place a link there. So Luca, shall we start with the demonstration and the exercise for manual calibration?
Regarding that, the link that I shared with you all, that is a new installer for Apex Qt. I just created, and that will fix all the issues that made me really struggling this morning. So please get that downloaded, and then in the meantime, we will install it again after Luca's session, and then we will continue with the Apex Qt session, until the end of the day. And then if we fall short of time, then I'll come back tomorrow morning to complete the Apex Qt session before jumping to the Apex Smart Flow session.
Okay, thanks,
Go
Jehan.
ahead. Yeah.
Luca, you're on.
Yep.
You're up.
Okay, then I'm gonna share my screen. I wanna share this one. And I wanna bring the chat also. Okay. So if you wanna try to follow these, I would like, let me ask these to Jack or Javier. How much time do we have? Are we planning to stop in about 1 hour and 20 minutes, something like that?
Yes, we have
Okay.
an hour and 20 minutes. So if that is the time you will spend, then that's fine.
No.
I can continue tomorrow. Otherwise, I will just, continue after you finish
Yeah,
the
no,
session.
no. I have a 4 steps exercise, so I will see if I, well, they can play a little bit. Okay, thank you. So in the folder that you have downloaded from the Google Drive, you have another folder called calibration example. Inside you will find a bunch of input files. And there is also the Apex editor tool that now you are familiar with. If you want, you can go ahead and open the tool, or if you have it open already, you can point to this folder. Why is it taking this long now? Okay. So enable the content because I have it already in the project folder. I can click on open, and this is going to read everything. So just to give you an overview, for this exercise, I've designed another management. This one is, I want to try to simulate a tomato field. So if we go to the management, we can get the file, and we have this test tomato nitrogen. So read the file, and here is our management with all the information. I've tried to, in this case, we have a bunch of years because I made these. I was trying to calibrate the model following data that were published in a scientific paper. So basically, I was trying to replicate what the scientists observed over there. So I create some kind of fake years, and then what we really need are basically year 16 and 17, because in this case we have 2 years of observation. But for this exercise, we don't need to play with the management. We played already quite a lot in the previous session. So what I want you to do for now is just run the model, and then let's play a little bit. Earlier today, I think Javier and probably also Jack yesterday, they show you where in the OUT file you can find the equation that is used to simulate the potential evapotranspiration. Please go ahead, and the first one that find it can type it on the chat. I'll give you a couple of minutes or less. As I say, it is in the OUT file that was generated when you just run the model. So this one is the file, and try to find it. Hopefully you are still with me. I'll give you some hint. You have to scroll a little bit down. You start see something about weather data. Okay, time is up. Okay, so right now the model is set to estimate the potential evapotranspiration using Penman-Monti. Here is the information. Is on line 282. And if we scroll all the way down at the very end of this file, we can find, first of all, important information. I don't remember if we ever mentioned these during this workshop. To understand if the run is complete, you can always open the OUT file, and if you have this timestamp here, you know that the run was complete. If this information is not printed, it means that something was not right in the simulation. So something happened and the model did not complete the simulation successfully. Okay, then over here we have this set of information, and we are going to use some of these for this exercise. These are average values for the entire simulation. And for now, I want you to look at these. This one is the potential evapotranspiration, the average potential evapotranspiration estimated for these in this simulation. Now, going back up, as I said, we are using Penman-Monti. I would like you to switch from Penman-Monti to Hargreaves. And you can switch Hargreaves from Apex Conf. If you scroll up, you have variable number 10 that said the equation that you want to use. And because we want to use Hargreaves for this example, we want to set it to 4. So go ahead, type 4. sorry, just to be sure, let's do this. Read, let's type right, and run the model again. Now you can go back just to be sure. We can go back to the OUT file, and we see that we are actually using Hargreaves. Now, if you go to the calibration example folder, I placed also another Excel file that is called calibration data. If you open it, I kind of made this up. Somehow it's made up. The values are more than reasonable. So let's say that in this place, the annual average potential evapotranspiration is 1,450 millimeters. Right now, if we go again at the very end of the OUT file, the model is simulating a little over 2,000 millimeters. So the model is overestimating the potential evapotranspiration. So let's start our process to calibrate the model with the potential evapotranspiration. That is kind of the driver of the water cycle. Okay, everything is good over there. And because we want to calibrate potential evapotranspiration. And if we go again up here, where we have the information about Hargreaves, we have also these little information that it says that parm 23 is set to 0.0032 and parm 34 is set to 0.6. So these two parameters are related to Hargreaves. You will find more information on the user manual. Now, I would like you to play a little bit, or, well, we don't have a lot of time, but basically, well, I'll try to do it slowly. Let's go to the parm file. Apex parm. Let's get the file. Mine is called parms. Let's read it. And I said we want to change parm 23 and parm 34. So let's start with parm. One is here, and the other one is here. So I don't know if we have enough time. My idea was, moreover, it's not that easy doing this remotely. When we teach in person, usually we give some time to the students to actually change the parameters, play a little bit, and we can have immediately a feedback from the students because we are there. We can see what they are doing.
Luca,
Probably, yes.
let's take time and then do the exercises. We have about an hour, until the end of the day. So why don't we just, get this thing, extended and completed, and then just call it a day there. And then tomorrow when we come back, I can actually, continue with the Apex Qt session tomorrow morning.
Okay, sounds good. Sounds good to me. So, since you have time to play a little bit with these, with the manual calibration, I would like you to use, so here in the Excel file with the calibration data, you have this value that is the observed, or let's say the average potential evapotranspiration. I want you to play a little bit with the model, changing the value of parm 23 and parm 34, trying to get a value that is close to what was observed. Keep in mind that here in the description you have the range for these values. So parm23 goes from 0.0023 to 0.0032. So don't put over there, over here, don't put 0.5. While parm34 goes from 0.5 to 0.6. So in this one, don't put something like 0.001 or 1.5. Okay, so let's say you can play with these couple of minutes. Yeah, let's say 2 minutes. And if you have any question while you are playing, just let me know or type in the chat. And oh, and one, yeah, this is while you are playing. This is well, let's say a sort of a strategy. Don't change more than one parameter at a time, because then it would be difficult to understand what's the effect of your change. So you want to change one parameter, look at the result, change another one, or change again the previous one. Let's say now, as I say, now the model is overestimating. Let's say you start changing, I don't know, parm23. So you reduce parm23 because you are already at the upper range, higher range. You reduce it, and let's say you realize that it is now too low, so you want to go back up a little bit. So you do this a couple of times, and then you switch to the other parameter, and that's the process of manual calibration. I know it's not, probably is not, well, definitely it is not fancy, but it really helps to understand the model. If you don't remember where to find the simulated potential evapotranspiration, open the OUT file, go to the very end, and then scroll up a little bit until you find these average annual values and look for PET. There we go. Are you having any problem? Everything going fine? Give me a thumbs up if you are with me. Okay, I can see one. Well, Javier, your thumbs up doesn't count. I really hope you are with me. Okay. Okay, there is a question. And my answer would be no. So the question is that with these two parameters we are changing, will alter ET reference and then ETP. Is it safe to say we might change, for instance, crop coefficient as well for the better? Usually, we suggest to change the general model parameters first, instead of playing with the plant parameters. And this is because, especially with some parameters that I will show you later. I've included these in my exercise. The risk is to get, we say that the risk is to get the right answer for the wrong reason. Because some of these parameters can act like a volume knob, especially I'm thinking about radiation use efficiency or harvest index. You can easily kind of increase the volume and you will get, most likely you will get more biomass, but you are not actually fixing the problem that is, for instance, giving you the low yield or the low biomass accumulation. So first you want to try to get everything else right, and then you might want to change some plant parameters. Does it make sense? Okay, now I will change these because I know, let's say I know the answer. I just, because I made all of these, obviously I know kind of probably the best combination. And for me, the best combination was setting these farm 23 to 0.0023, while farm 34 was 0.58. So it was a big change for farm 23 and a small change for farm 34. So let's write these, run the model. I'll update these. And now my PT is this. So 1427. That if I compare against these, I'm obviously very close. Obviously, because I've, as I say, I've just kind of created these. I want to just give you a demonstration. Now, in my publication, the publication that I use to create this exercise, they provide information about the irrigation. Let's say they say that they set up the irrigation according to the evapotranspiration that was estimated. So what I did, I tried to create an irrigation scheme that was able to be close to these values. So what can I do to understand if the irrigation I have created is close to these values? I can go to back to my tool, and we saw this before. If I open the SUI file, get the file, tomato, and I read it. As I say, I'm interested in the last 2 years of my simulation. Basically, I'm using the first 15 years as a warm-up period or clean-up period, and the last 2 are the one I'm interested in. And if I go to the column with irrigation, here are the values that basically the amount of water that I'm applying. For this, let's say this one, there is nothing about calibration, but I want to stress out the concept that if you introduce irrigation and your irrigation, the volume that you are applying is wrong, then it's going to be basically impossible to calibrate the model. So before going to calibration, you want to check all your input data. So let's copy this. And if we put this over here, and there is no statistical analysis here. It's just, we are just comparing numbers, no, nothing else. So those values, where was it? Oh yes, it was. There was a publication with the average values for potential evapotranspiration in US. So I picked a place that was close to the experimental station, and it was around 1450. Someone could explain. Well, yeah, we will see about that. So moving on with this exercise. So for now, I'll show you what you can do to control your simulation. Like, I don't want to use pen-mount heat, I want to use our grade, for instance, because I don't have information about the wind speed, so it doesn't make sense to use pen-mount heat. So you switch the model, you set up the model to use our grade. And then you change some parameters that are related to the Hargreaves equation to estimate the potential evapotranspiration. And now we just check if our management correctly replicate what happened in the real world. Now let's see something else. For instance, one check that you can do, and this one is absolutely an example. Let's say that you know from experiment, from research in that area, that usually, so let's look at these two numbers. You know that usually the volatilization is about 10% of the nitrification. If we look at the result right now, they are about the same. Actually, they are exactly the same. Now, I will point to the right place. If you go to the parm file or the parm table, parm. Okay, we have parm number 72 that actually affect the ratio between volatilization and nitrification. I want you to change this parameter here, trying to get a volatilization that is about 10% of the nitrification. And you have again a couple of minutes to do this. Let's see. Yeah, Jack and Javier already replied to some question over there. So for a question related to, is not strictly related to calibration. Actually, it's not related to calibration, but while we wait a couple of minutes. So SW is soil water. So basically it's the soil water content. And most likely, well, it is strange that you have 0 in your data. I don't know why. You should have a very high water stress for your crop, if any crop is growing over there. Most likely you are not seeing the ASA output file because it's not printed at this time. I'll show you a little bit. Well, after this, I can show you how to print also the ASA output file. So, anyone got some or had any luck changing Parm 72?
While they work with it, can I share my screen? I'm just quickly show him how to do print ASA output.
Go ahead.
Yeah. Give me just 1 second. I need to bring my computer up. Let me share the screen. So the way you print and you tell the model to print any output is you go to the Apex print that, and on top you are going to see which variables do you want to include in the outputs. However, if you go down, not that much, here, you will see that you have the different options. So in the case of whoever wants to print as a file, this might be 0. Just type a 1, or in this case, as Luca is doing it, 4, type a 4, write the file, and then run the model. And then when you go and check your outputs, was this thing? Yes. The ASA output is going to be displayed there. If you want to add any of these other outputs to your simulation, then you just either do this a 4, a 1 will do it. I always prefer to use 1 as a flag. 1 is yes, 0 is no. So, and in this case, I change it, I write it, I run it, and it works. So if you just need to add any of these outputs, you can do it. Just be mindful that there's no purpose in printing out everything. You just need to choose, with the help of the manual, which are the outputs that are useful and are going to provide information. If you are not going to work with any of these, then just don't print them out. But to show the impact, first we need to get rid of the outputs. If not, you are going to have a legacy problem here. So delete it. And then when you run it, this SAD and WSS will not show. And obviously it takes time. There's none of these files showing in as my outputs. Now, if you want to open this, you will have to use a text editor, and then you can extract the data that you need. That's the way you decide which outputs do you want to print and which outputs you don't want to print. Back to you, Luca.
Thank you, Javier. Okay, we are back. So we were working with Parm 72 that, because I prepared these before, I know that I can get good result with a value of 0.1. So I can write this, run the model. I can go back here, and now I can compare these two values. And I'm trying to get close to volatilization being about 10% of nitrification. So these, let me stop sharing. Well, I can keep everything there. So these are just, let's say it's just one step. In this case, we are saying that we know something about nitrification and volatilization because we have some observation and we decide to change that parameter. If you have information about, I don't know, runoff or sediment yield, you want to use the user manual to find out which parameters are somehow related to runoff or sediment yield, and you want to start playing with them to try to calibrate the model. Keep in mind that process like soil erosion can be affected by processes that are not directly related. Well, can be affected by parameters that are not directly related to soil erosion. For instance, you can affect soil erosion changing parameters that are related to crop growth, because obviously if the plant grows more or less, is going to affect how much biomass is on top of the soil, and the consequence is going to affect runoff, therefore soil erosion. So the process that you have done right now for just one parameters for nitrification and volatilization and two parameters for the potential evapotranspiration can be repeated for all other process that you know, process that you have information about. You may have measurement, you may have information about leaf area index, crop yield, all these kind of things that can be measured. Or you might have information about average yield in an area. So you don't have an exact measurement, but you know that average yield of corn in, I don't know, Ohio is in bushels, or I guess 10 bushels per acre, something like that. Do the conversion to kilograms hectare because everything from Apex is metric unit, and everything related to biomass yield is dry weight. So when you are trying to calibrate the model, keep in mind that the output of the model are dry weight. Now, let's do this. Let's go to the ACY, because now we try to calibrate something related to the plant. Because if you look at the calibration data spreadsheet, basically in the publication that I use, the authors provide information about the above ground biomass and the yield. So let's find out this information, so above ground biomass and yield. Let's start with the easy one, yield. Yield is directly from here. We can go to the ACY output file in our editor, columns YLDG. We want to use the last 2 years. So if I copy these two and I paste it over here, we see that, okay, we are close, but not, let's say, probably we can do better than this. While for the above ground biomass, this is going to be a little bit more, well, I don't want to say complicated, but it's not going to be as easy as for the crop yield, because we have to find this information, or for this example, this information in the OUT file. So you have a way to explore also the OUT file. So if you keep scrolling up, sorry, let me go back here. So we have the average monthly values here, where we found our PET. We can find several other information. If you scroll up, you will find here some information about balances. Jack yesterday mentioned these. If we keep scrolling, okay, now we arrive here. You see here 2008, so the last year of our simulation. And we have some information reported monthly, so month by month. And we want to look at this row here, STL. That is standing live biomass that corresponds to the above ground biomass. And we see that in July, the maximum value was 15.42. So let's grab just, let's say 15, and we put 15 here. And then we can keep scrolling up, and we reach 2007. And again, standing live is 14. Let's put here 14. Okay, so now we have this situation. The above ground biomass that is overestimated, and the yield that is underestimated. Okay, so I'm showing you these, but as I said before, don't go to modify crop parameters as a first result. It shouldn't be the first thing that you do to calibrate the model. But I want to give you this example to understand what you can do with the model in some situations, or also let you understand why you want to modify some crop parameters. So let's think about above ground biomass, and let's go to our crop table. No, sorry, let me go first to my management. Where is my management? Okay. Plant ID is 180. Plant. If I scroll down to 180, I have processing tomatoes. And if I remember correctly, up here we have also another, there we go, tomato. So let's say we realize that in the experiment that we are trying to replicate, it was used a different variety of tomato. So it's not this one, it's something different. So this is the case when you want to change some plant parameters because you are using a different variety, different corn hybrid, for instance, that has a different potential leaf area index, or those varieties that are called stay green. So basically with the leaves that stays green for a longer period of time. So you want to change some of these parameters in some case. So let's say in this case, we know that the model is overestimating our above ground biomass. So probably this means, or let's assume that everything else is correct in our simulation. We have checked everything else, everything makes sense, just the model keep overestimating the above ground biomass. What we can do, we know we are using a different variety in our experiment. We can change the WA, so the biomass energy ratio. That is the same concept of the radiation use efficiency. So let's say I'm gonna change this for you. Right now we have 30. We wanna reduce it to get, let's say, a decent value. After testing a couple of times, let's say actually I can do this for you. Let's do this. Let's see what happens if I put it 20. I'm taking a risk here because I didn't try. So let's run the model. Let's go here. I have standing live in 2007. In July, there is 8.9. So, 9, while in 2008, standing live is 9.8. So changing the radiation use efficiency from 30 to 20, it reduced way too much the above ground biomass accumulated by the crop. So it should be a value in between. And because I played, let's assume we are doing this a couple of times, back and forth. I try to different values, and then I decide to try 27. I write and run the model. And now I have standing live in 2007 equal to 12.7. So this. And in 2008, I have 13.7. And let's assume we run our statistics and we say, okay, now my results are at least acceptable, if not good. As Javier explained, I have to fix my minimum standard ahead. It's not like, oh, I cannot get anything better than this, then I consider this good. Okay? So now let's say we have calibrated our above ground biomass because I've adjusted somehow, I've started adjusting my my crop to the variety that was used in the experimental field. But now we have changed the above ground biomass. What happened to the yield? For the yield, we know that it's much easier to use the tool. Let's read these. Let's put these two values. In here, and I see that, okay, now I have my above ground biomass that is reasonably close to what was observed, but my yield is still very low. I can let's assume I do some research about the variety that I'm using, or the variety that was used in the experimental field, Apex plant, and I discovered that that specific variety is characterized by a very high harvest index. Is a dwarf plant, so very short, that is able to produce a high number of fruit, this kind of stuff. So I can start playing with the harvest index because I want to replicate the characteristics of that plant. So I start playing with it, and as before, I can go, obviously in this case, I have to go higher. I try a couple of times, and then I tried 0.7. I write this value, run the model again, and let's see what happens to my yield with this value. Let's read this. I can these two values here. I can go over here. I can paste it. And I can see that I'm able to get much better results. Again, I run my statistics, and keep in mind, every time you that you run the statistics, you want to run the statistics for all the variables that you are trying to calibrate, all the observation that you have. Because as I showed you before, I can change something about to change the above ground biomass, and this is going to affect something else in my simulation. So every time you want to consider everything. So this is all I have for this exercise. Is there any Any question or something that was not clear in this exercise? Or something, I don't know, Jack or Javier, if you want to add something to this.
Well, excellent. I've been busy just answering those questions, coming up in the chat.
I can see that they were popping up. So
Right.
okay. So I guess you can go ahead.
This is a perfect time to just stop here the sessions for today, and then we can spend a few minutes to address whatever questions you may have before wrapping up today. So you can unmute. Is it possible for the participants to unmute? If you can unmute yourself, then you can just speak to the microphone, and then just we can just talk directly for any questions to address.
Luca, what would you recommend if, what parameters would you recommend to adjust if the yield is too high as opposed to too low?
Well, first of all, you want to understand why the yield is too high. Because, for instance, let's say I can think maybe you are applying too much fertilizer or too much water compared to what was the real world. And these can, so basically in your simulation, the plant is suffering a lower stress compared to the real world. Or it can be, I don't know, the evapotranspiration. There are many things. I cannot tell you, oh, you have to change this unique parameter and everything will be just right. It really depends by the situation.
Yeah, that's actually that explains the nature of Apex in a way. The beauty of the Apex, the way that I see, is that it incorporates a pretty good crop model and hydrology model, and then also nutrient dynamics model as well into a single modeling platform. So the interactive, processes between these, components of the model make it nonlinear for pretty much all processes occurring in the watershed or cropping systems. So there's always factors that are not straightforward, and maybe we cannot just easily pick up until we really read outputs and then digest various dimensions of the Apex outputs until figuring out what's causing really this all the way down from weather or management practices. So that's why we are calling Apex as a decision support tool in a way.
If I can add something, just something else that came to my mind, you can have, in your simulation, your yield can be overestimated also, for instance, two reasons, somehow related. Let's say you have soil data that are not precise, and you have a very deep soil as input data, while in the real world that the soil is shallow. So in your simulation, more water will be available for the plant compared to the real world, or somehow related. In the real world, you have a deep soil, but the plant that you have there in the real world has a root system that is not able to go very deep, so it's not able to access the water and the nutrients that are deep in the soil. While in the model, the plant that you are using has the ability to go very, very deep in the soil, so it's able to access those resources, and that's why it's giving you, for instance, that high yield. As you can see, there are many things all connected that makes almost impossible to give you just one answer.
That's right. I mean, various commercial crop varieties, let's say corn, we call it corn, and one crop there in the crop table, but actually there are a number of different, inbred lines that are available for hybrid production. So some are more like a drought resistant, some others are heat resistant, some others are pest resistant. All those, particular properties of different varieties, we can't really, replicate those variety specific properties of the corn. So if you know the particular, generic properties of that particular variety that you're simulating at your field, then you can modify the corn parameters as such, and then can expect a better result from the Apex model.
Someone on the chat asked for the link to download the folder on Google Drive. I put the link again in the chat now, so they don't have to. You don't have to scroll up. It's there again.
That's an interesting question. Well, let me. Temperature and solar radiation, can they be affected by management practices?
You want me to answer? Yeah.
Well, the answer is no.
Is no. Yeah, those two, temp and solar radiation, they are basically is an average of your input data or the generated data, if the model is generating weather data for you. But there is no way you can affect air temperature with a management practice or the solar radiation.
One thing that I can tell you about this is that these solar radiation and air temperature values, their effect on crop growth or water quantity quality simulation, nutrient dynamics can be influenced by management practices, of course. Well, for example, soil temperature, is a key variable that determines winter soil root zone hydrology and also microbial activities in the spring season, early spring season. And based on the land management, let's say residue management or mulching, or those will influence the surface land cover, and therefore snowpack sitting on the soil will have less impact, and then also air temperature will not be that strongly connected if you have greater amount of surface residue on the soil than the situation where you have less or no residue sitting on the surface.
So, Jehak, this is Srini again. So I had another general question. I mean, like you just mentioned about, the, I mean, I also like, Apex a lot. I mean, so I was wondering about, like, your comment about soil carbon sequestration, like how good the model is in terms of, that. And do you also have any plans to, or it has already been used, to predict greenhouse gas emissions, GHGs?
I believe Luca has a pretty good answer to that.
Okay.
Sorry, can you repeat? I was reading some question.
I can answer that then.
Sorry.
Well, let me tell you what we have now with the current Apex model. So the current Apex model simulates, like I said, carbon dioxide emission and also sequestration through, photosynthesis. That's what's currently available for CO2. And I already, talked about what the processes are involved with CO2 emission, right? Another greenhouse gas component is nitrogen. So nitric oxide is calculated as a result of the denitrification. So in soils, hydric soils or saturated soils where you have nitrate abundant in the soil, that nitrate will actually be denitrified into nitric oxide by anaerobic, microorganisms. And that's the process of denitrification. And then nitric oxide gas will be emitted as a result of the denitrification. Another thing that is planned for the next 2 years, I should say. And I can tell you this is planned because this is just approved. It's a part of a project that is approved for funding. In that project, we will be adapting from the DNDC model, the way that the DNDC model estimates methane emission from saturated soil. So that will mostly be applicable to wetlands or rice paddies or quite hydric soils. So those with that, if we add methane into the equation, then that means that we have more complete carbon, calculation, complete cycling of carbon, especially in those, water abundant environment. We recently added a more rigorous, module. That's a numerical solution to calculate a nitric oxide emission from soils, which is different from the denitrification module we had in the EPIC and the old version of Apex. So that is a work done by Cesar Israeldi, and Cesar's work has been added to the Apex model, so it can be activated, enabled as an option to simulate denitrification processes. The catch is that because it's a numerical server, it's computationally demanding. If you turn it on for denitrification calculation, then it's gonna slow down the Apex run quite a bit, visibly. So that's the only catch. To do all the numerical, iterations, it's like the Richards equation we recently added to the Apex model for the beta zone, percolation calculation. Richards equation is known to be the model for unsaturated flow. But unfortunately, it can only be solved using numerical methods, and therefore the method we adopted in the Apex model also relying on the numerical methods. It slows down notably the Apex runs, and it can be several times more time than when they are turned off. So there's a trade-off, between.
So in this current version, that Richards equation can be turned on.
Yes.
Okay.
Yes. In the
That's
apex cont.dat file, we have a flag called what is it? IPKR. You can set it with the integer value. What is it? 2? Look at.
I can find
Something
it.
like that. You can find it from the Apex editor, and then you set it that way. Then it will actually enable the recharge method.
So right now it uses Century, right? For the carbon, simulation.
Yes.
Yeah.
Right. Century is the default, if I remember right, for carbon calculation. But alternative method is the Phoenix method that we have. But would recommend to use the Century.
Century. Yeah.
Yep.
Okay, thank you.
Mm-hmm. Yeah, sorry, I missed that question too. I was I was answering it to another question on
Sure.
the
Yeah.
chat.
That was good. It's fine. All right. Do we have any other questions? Cool. All right, then. Oh, you mean question, obviously, or Gansham? Luca, you're muted, I guess.
Yeah, sorry. No, I think it was that was a conversation I was having. So
Okay.
is yes, obviously, to my answer.
Okay. All right. If you don't have any more question you want to address today.
One more questions, Zia.
Mhm.
So for the grazing component, actually, so I think Apex Graze or something, right? I mean, so is that also, I mean, can we also operate it through the Apex editor?
Yes and no, right? Yes and no.
Yes
Meaning
and no.
we have another version
Okay.
of Apex Editor for that. So
I,
you can use it, but not this particular one that we're using for the workshop is available. I mean, it can run Apex Grace because Apex Grace have introduced a new set of inputs to better simulate the grazing practices and other components relating to rangeland simulation. So that was the version that's modified from the standard 1501.
it does it also work with this 15 version,
No,
1506? Like
1501
Apex,
version is different
yeah.
from Apex
Sorry.
Grace. What I didn't really mention earlier is that we have, as you saw, this Apex Grace being a different version from Apex 1501, and then we have another version called Apex 1307, which is a modified version for SIP cropland simulations. And these different versions have evolved with all the new routines that helps better simulate those related processes. We have been maintaining several different versions. Um, now, now it was a couple 3 years ago since we started to make an effort to kind of merge all these different versions into a single version. That include Apex 1501, Apex 1605, which is Apex Grace, and then Apex 1307, which is seed cropland version Apex. They've been being developed separately over I don't know how many years, like many years. And now we actually made an effort to merge all of them together. And then now we have a consolidated version of Apex now that contain all these different three versions, and we call it Apex 1905. So where's 1905? We do have 1905 version. The thing is that even though we are more than eager to, I mean, we are eager to really, make this 1905 version to be the new current version that will replace 1501. Our software development has been going much slower than the model development. So when the model is just running away from 1501 to 1905 with all these new inputs and new modules and functionalities, our tools, including ArcApex, WinApex, and Apex Editor was a little better because we do have a 1905 version, new an editor version for the newer Apex. But the ArcApex and WinApex are a different story, and we've been trying to catch up with these tool interface tools even with the 1501 version, because we've been updating 1501 over time. We've been going much slower with these software programs.
I
So,
know, yeah, it's very challenging,
but this
we
year,
appreciate, the team, the Temple team, in maintaining these excellent models, actually. So,
Thank you.
so
I want to echo Serene. Oh, Serene, go ahead. Sorry.
yeah, can I have a version of that 1605 Apex Grace and Apex Editor version for that?
Yes. Well, I would recommend that you actually use 1905 because
Oh,
that
okay,
includes 60, I
everything.
mean, Apex Grays already.
Okay, and so that would be available for use, I mean, shortly, or
Yes. Yes.
it's
Yeah. We have the code, and then we have an example, in set of input files. We have the editor available for it, but we have not been distributing the 1905 just because we are not ready from the
so
user's standpoint.
so the beta version kind of
The
beta version is
1805 is current. It is complete.
1905. Okay.
Yeah, yeah. It's just a WinApex. We don't have WinApex program for 1905. We don't have
Oh,
ArcApex for 1905 yet,
oh, okay.
but we are
So
going to
then,
get it soon.
okay, so the Arc Apex version of 1905, you expect it to be available soon?
Hopefully soon.
So right now, if someone has to use that version, so what, like, so we have to work, use it like like using the Arc editor, or maybe from the
Yes,
command
yeah.
prompt?
Just right. Just some text files, editor, and so forth.
Okay,
Oh yeah,
thank you.
I mean, I recently updated Apex Qt for 1905. So yeah, I was
Oh,
not right.
that's good.
Apex Qt is available.
That's good. I will be in touch with you. Yeah. And
Sure.
thank you, Javier, and then Luca and Susan, and then you, for well, excellent. These lectures and training is very useful. I commend you all. Yeah.
Thank you. Thank you. I appreciate it.
Yeah, thank you. This is great. I echo what Serene said. Jehak, are you going to do an example where you show how we can plug Apex into one of SWAT's sub watersheds?
I didn't hear you well. Can you repeat the question?
Yesterday you said that, if you're running SWAT, for example,
Oh,
there's
Apex and
an
SWAT integration.
agriculture area, you can plug SWAT as one of the sub watersheds.
Yeah, I mean, I can do that.
Or
It
do you
was
do you have it documented somewhere in
yes. Arc Apex user manual has a section that describes what it takes to, use Arc Apex to make a SWAT integration. Um, yeah, I wasn't really getting any response about it.
Yeah,
Uh,
yeah, yeah. I didn't even know you can do it. It was interesting when you
right.
mentioned it.
Yeah. And it's not a lot of time to do that, but um, I already have Apex Qt session
Yeah, yeah,
postponed
yeah. The,
tomorrow.
well,
That's a bit
I
exciting.
can follow up with you on that other stuff offline.
Yes, yeah, yeah. If you and others want this demonstration, be part of the workshop, then I'm more than happy to make a short video clip on it and then distribute it along with other sessions. Or you can actually um, go to the Arc Apex user manual and then look for the SWAT integration. Then you will find a session. I think it's like appendix or something later in the user manual book where you can find how to do the Apex integration into the SWAT model.
Great, thanks.
Mhm. Okay. Very good. Well, thank you everyone for staying around, and uh, thank you all the instructors for the excellent lecture today. We learned a lot today, so hopefully you review what we've learned so far today when you go back home, and then when you come back tomorrow, you're ready for another topic tomorrow. So we will gonna start with Apex Qt tomorrow morning for an hour or no more than 2 hours in the morning, the first thing, before starting to learn how to incorporate, how to integrate ModFlow model into Apex, and then simulate coupled surface subsurface hydrology, nutrient transport from the soil root zone into the aquifer back to the ridge, and then brief overview of parameter estimation tool for calibrating Apex ModFlow model. Thank you very much.
Wonderful. Thank you.
All right.
Thank you all.
Thank you.
Bye.
Bye.
Bye-bye.